Okay, short little lecture on Chapter 14, Periodic Motion. So first of all, what is periodic motion and what causes it? Well, periodic motion is motion that tends to repeat itself. Examples would be, as you can see over here, a mass on a spring. If you take the spring and you take the mass on the spring, you pull it back and you release it, it's going to essentially go boing, passing over some equilibrium point and essentially retracing its path, having what we call an oscillation. Other examples would be the swinging pendulum on a grandfather clock. That type of motion is going to repeat itself, so that would also be this oscillating motion or periodic motion. Now, what causes this? We need to essentially have a restoring force that is going to tend to pull an object back to its equilibrium position or its at rest position. Looking at the case of the mass on a spring, we know that the equilibrium position is going to be shown right here at B, which is the string at its unstretched length, just kind of sitting there with the mass attached to it. Now if I take the mass or the cart and I pull it to the right, I know that the spring is going to pull back on me towards the left, towards its equilibrium position. So we're going to have this force that's called a restoring force. In this case, it's just the spring force. On the other side of the house, where if I take on the other side of the equilibrium point, if I now compress the spring and I push on it, the restoring force is going to be in the opposite direction, again pointing back towards the equilibrium position. Since the force always returns to the equilibrium, or always wants to return the mass to the equilibrium position, the mass on a spring is an excellent example of what causes periodic motion, simply a restoring force that points back to the equilibrium position. So let's just get some definitions out of the way for some of the characteristics that we're going to see with periodic motion. If we wanted to consider a mass on a spring, so here we have the spring at its unstretched length, so that would be its, x0 point, if you will. And if I take this spring and I now stretch it out such that I pull the mass such that now it has covered some distance. Normally I would call that distance A, or call that distance x. Here in this case, I'm going to call this the amplitude, which is going to be the maximum magnitude of displacement from the equilibrium position. And in a perfectly frictionless world, you can see how this mass would simply come and compress the spring just like that, and we would have the same amplitude on each side there. So there's my negative A. So A is the maximum displacement. T is going to be called the period, and that is the time that it takes for one full cycle. So for the mass on a spring, if I take that mass and I pull it out to this point that I'm calling point 1 here, it needs to go all the way back past the equilibrium position to the maximum compression, and then come all the way back to its starting position. That's going to be the period, or the time for it to complete one full cycle. It's very easy to get confused with 1/2 of the cycle. Remember, it has to return to its original position. The frequency is simply going to be how many cycles does it produce per unit time. Does it go really, really fast, or does it go really, really slow? The angular frequency, sometimes it's useful to talk about this in a angular sense, is going to be related to the frequency as such. And for that, you can imagine something like a record, and we have a point on a record. That point is going to go around the record. It's going to go around it once, it's going to go around it twice, it's going to go around it 3 times. So relating the angular frequency to the number of cycles per unit time. And last but not least, the frequency and period are related to each other, and actually inversely, the frequency is 1 over the period, and also the period is 1 over the frequency, where frequency is number of cycles per unit second, and the period is going to be the time for one cycle. So you can kind of see how the units will work out on that one. If the restoring force is directly proportional to how far you stretch it from the equilibrium point, it's going to be called a special type of periodic motion. It's going to be called simple harmonic motion, where essentially that means we have the simplest possible force, a linear force. Hooke's law is going to describe a spring where we say the force is equal to negative kx, and you can see that the force is indeed proportional to its displacement from equilibrium. So a spring is going to produce a type of motion called simple harmonic motion. You can see a plot here of the force versus the displacement for a spring. Now, in the real world, we know if you stretch a spring too far into that plastic region, that the restoring force is not going to quite be linear. However, in the regime that we're interested in, it is indeed going to be linear, so we can say that a spring is going to obey simple harmonic motion. For a spring that is oscillating back and forth about its equilibrium point, those characteristics, the angular frequency, and period, and amplitude, are related to two things. It depends on the spring constant k, how stretchy the spring is, as well as the mass of an object, how much inertia does the spring have to overcome. So we can relate these characteristic parameters that I described to the spring constant as well as the mass. We can say that the angular frequency is going to be the spring constant divided by the mass. The frequency is going to be 1 over 2 pi square root of k, or spring constant, divided by mass. And the period is simply going to be 1 over that, or 2 pi square root of m over k. If we look at example 14.2, it says go ahead and calculate out what these parameters are. It says you have to apply a force of 6 newtons to stretch the spring out to 0.3 meters. What that lets you do is it says you can figure out what your spring constant is. You know that the spring constant is going to be the force divided by the displacement, or in this case 6 newtons divided by 0.03 meters. So we get our spring constant to be 200 newtons per meter. Now suppose I want to go ahead and I want to calculate the angular frequency here. I would say that the angular frequency is going to be the square root of that spring constant k, which is 200, divided by the mass, 0.5 kilograms. And I'm going to come up with the angular frequency of 20 radians per second. I can now say that the frequency is going to be the angular frequency divided by 2 pi. So the frequency is going to be the angular frequency divided by 2 pi, or 20 radians per second divided by 2 pi. I come up with my frequency to be 3.2 cycles per second, which is also going to be a unit of hertz. And last but not least, the period is simply the inverse of the frequency, so it's going to be 1 divided by 3.2 hertz, or 0.31 seconds. So it takes that mass 0.31 seconds to go from its starting position to the other side of the equilibrium position, and then all the way back. If I took a look at the plot of the position versus time for my mass on the spring, what I would see is I would see some sinusoidal behavior, and we could actually write that position versus time using a cosine, where the position is going to have some amplitude associated with it, how far at the maximum displacement from the equilibrium. It's going to be related to the angular frequency, which is related to the mass and the spring constant. The dependent variable is time. And lastly, there's simply a phase angle which says, hey, what point in this object's motion was at time is equal to 0, and just shifts the sinusoid from the right to the left a little bit. So we can just kind of look at this graph right here, and we can say, okay, at time is equal to 0, it was at its maximum position, so that phase shift is going to be 0. And how long it takes that object to return to that same position, the maximum displacement from equilibrium, that distance right there is going to be the period. You can kind of see graphically where the period is here. And at the maximum, we're going to have the position be equal to the amplitude. And we can relate the period to the frequency, simply reciprocal, as well as the angular frequency, the frequency divided by 2π. Changing the mass, changing the amplitude, or changing the spring constant is going to, of course, modify what this graph looks like. If we increase the mass, then what we're doing is we are changing the angular frequency right there and increasing it from a value of 1 to a value of 2 to a value of 3. What that's saying is it's taking the spring longer and longer to complete one full oscillation, essentially because we've increased the mass and the spring has more inertia to overcome. If we kept the amplitude and the mass the same and we increased the stiffness of the spring, increasing the stiffness of the spring, intuitively you would think, okay, that's going to make the spring oscillate back and forth more quickly because it's going to have more strength to it, if you will. So going from 1 to 2 to 3, you can see that it does indeed oscillate the mass back and forth more quickly. One thing to note is for simple harmonic motion, the amplitude is unaffected by these two changes. If we increase the amplitude and have the same values for the mass and the spring constant, it's not going to change the angular frequency at all. It's simply changing how far you stretch the spring away from equilibrium, and you can see changing the amplitude from 1 to 2 to 3 is not going to affect the period or the angular frequency. It's just going to affect how the maximum displacement. Since we have our position constantly changing and we know how our position is going to behave as a function of time, we know that velocity is going to also change as a function of time because the position is constantly changing. And at this point you know that the velocity is going to be the derivative of x with respect to time. I know you can take derivatives now, so taking the derivative of the sine, or the derivative of the cosine, is going to give you a negative omega from the inside there, and then it's going to change the cosine to a sine, so we can write the velocity as such, and we can say that the acceleration is now going to be the derivative of velocity with respect to time. We can take the derivative of this guy now, and we're going to end up with an expression for our acceleration as a function of time now. Energy in simple harmonic motion, we know that the total mechanical energy is always going to be conserved, so we can write our total mechanical energy to be the sum of the kinetic energy of the moving mass plus the potential energy of the spring. So the total energy of the system at any given point can be written as 1/2 mass times velocity is equal to 1/2 k x squared, where that's the spring component. And at the extreme, we know that all of it's going to be potential energy of the spring. The mass would not be moving at that point, so we could say it's the total energy of the system is going to be 1/2 k a squared. And again, the energy can slosh back and forth between the mass's velocity and inside of the spring, but always conserved. The simple pendulum can also give us simple harmonic motion if we consider only small displacements from the equilibrium position. If we look at a pendulum here and we take the pendulum bob and we swing it out to some angle, we're going to get a restoring force of mass times gravity times sine of the theta. So the restoring force is going to be mass times gravity times sine of theta. And for very, very small angles, we can say that this is going to be roughly mass times gravity times theta, where essentially we've done a Taylor expansion and taken just the first term here, only valid for small angles. But you can see how the force is going to be proportional to the displacement away from the equilibrium, and if I were to bring my pendulum over here, the force would be pointing back to the equilibrium position. So we can say, in this case, the simple pendulum is going to also have simple harmonic motion. The period and angular frequency are going to be related to two things. It's going to be related to how long that pendulum bob is. The longer it is, the longer the period is going to be, as well as gravity. I mean, if you took this same pendulum to the moon, it's going to have a different period. It's going to swing back and forth a little bit slower. So we can write the angular frequency to be the square root of gravity divided by the length. We can write the frequency of a pendulum to be omega divided by 2 pi. So essentially 1 over 2 pi, square root of gravity divided by length. And lastly, the period of a pendulum is going to be 1 divided by the frequency, or 2 pi, the square root of L divided by G. And for some reason, this is the one that I always remember, and then I can convert between them. In the real world, we have these forces called friction, and we know that the amplitude is going to decrease over time. It's actually going to decrease exponentially over time, depending on essentially how strong this damping force is. So this type of motion, where we're looking at the position versus time, is a damped oscillation. And you can kind of see in blue here we have the amplitude getting smaller and smaller and smaller with a fairly weak damping force. And in the purple here we have a much stronger damping force. The amplitude dives off a lot faster.